Hello and welcome back to compiler programming. In the last episode we did this refactoring where now all the functions within one test are laid out together in memory one after another, and this was done in preparation for supporting what is called REAP relative addressing. Before we jump into the implementation, let me first do a quick explanation of what it is and why do we need it at all and why it was added to the instruction set, because REAP relative addressing was actually only introduced with the 64-bit version, so x86 64, and in 32-bit mode it wasn't there. And one of the reasons for adding this addressing mode is security. So let's talk about this a bit. When we have our a.exe, right? So we have some kind of executable file. When the system wants to execute it, let's start with the fact that executable file is just a binary file that contains several sections, as I also talked about last time. So it contains code, it contains data, and let's say miscellaneous information, but doesn't really matter for us for now. Let's just focus on these two. And originally, when computers were just starting out, the code in here would reference the data in here by absolute addresses. So in executable, there would be maybe in this miss section something like load address. And when the Windows or another system like Linux, they have slightly different formats for executable, but the gist is the same. You say, okay, when you load this process into memory, I want to be at the very specific, loaded at the very specific starting address. So when the code, for example, says move whatever, so it says move EAX, and then, for example, like so, and then move to, I don't know, ECX, whatever is at that location, right? So we are, with these two commands, we are loading whatever was this address in the memory. And this number would literally be just hard-coded in there. So it would expect that data would be loaded at the right address to be able to do this. And function calls were done in exactly the same way. So like you would have call 0x, whatever, 20,000. This is just how the code would be. And the problem with that is that would make it very easy for external processes to figure out at which locations to probe the memory, or if you had some security issues inside of your process that allowed to execute arbitrary code, whatever, you would end up like knowing exactly what is the layout of the memory and where to look for things. With 64 bits, they introduced this relative addressing. So your executable can no longer say, at least, I mean, it can say, but it may not be respected, or it really depends on how the system is set up. But let's just say that there is no load address anymore. So that means that you can't really use these kind of absolute values, right? If you don't know where to start, how do you know which value to put into here? Like what do you do here? So instead, what is happening is whenever the executable is loaded into the memory, the layout that was pre-specified here is mirrored sort of exactly in memory, but the offset here is always different. However, if layout is always the same, that means that if we have some kind of instructions over here, so let's say this move is now over here, and then we have this data over here, then this distance will always be the same, because this is how it was laid out in our file, and it was just loaded memory. That means that like this distance is fixed, but the base of it depends on basically where this instruction is. But we do know where this instruction is because the processor is currently executing this instruction, and the kind of the pointer to the currently executed instruction is called instruction pointer. And in 64 bits, you always add this R prefix. So this is why you have this RIP relative addressing. So this is all it is, that you have this instruction pointer that talks about which instruction I'm running, and we are using this offset as a relative from that place. And that's all that is that it's used for both calling local functions, like the functions that you specified in your code, and for loading some data, whether it's constant or non-constant data that you have in your application. We will start probably with constant data to try this out, but first we will need to support encoding at all. And the way we are gonna focus on it is actually through calls, because if you have like function A here, right, and function B, we can very easily define them. And if we have B calling A, then we can express the address of A as reap minus something constant, and do this kind of calculation. This is not very useful for us because with JIT we do know exactly where things are loaded in, but as that it will be eventually important when we move to the to outputting these to executables. And also I think it's can be nice for us for constant data, but we could do constant data otherwise as well. So this is not really that important, but let's dive right in. Okay, we move on from the printing setup to the code. To show you what it looks like in assembly, I actually had to jump to a different debugger, so Remedy, which we used in the beginning of the series. And here, I don't think I can zoom, unfortunately, the font, text font. Actually, maybe I can. Yeah, so let me do that. So now I can have slightly larger stuff. Okay. Where am I? Doesn't really matter where I am as long as I can find what I'm looking for, which is, come on there. Okay, maybe let me restart this. Yeah, okay, so this is what I was looking for. So this is the example of instruction that we will be doing, more precisely this one. So this, I think a value is function, is our local function. So if we step till here, right? Maybe checker is local function. Let me think about this. Now, I believe this is value as function, right? So like this reap plus is 9DA75. We can even calculate what that is if we copy this value and put it in watch and put it as hex. Oops. As hex. So this is going to be this address, 7F36. So this is somewhere quite far from where we are. So I'm not sure we'll be able to jump to it, but it's just like, this is the address that we will call. And this is what we want to encode. Good. So now we know what we are doing. And I can at least minimize this stuff and see where we are. Okay, so the next thing is figure out how do we actually encode this. To do that, we open up Intel architecture manual, and there is a very small section about RIP relative addressing that tells you how to encode it. So we already have this mod rm byte encoding, and let me try to rearrange it so that we can see more of this stuff and have it at the same time. I'm here encoding. Okay. So maybe like so. Yeah, that seems good. So we have mod rm byte, and it says that the mode has to be 0. So that is, I guess, this one. Yeah. Then we put rm as 101, and that would be where is it? It's probably in value h, if I'm not mistaken. Yeah. So it takes over the position of RBP. Like you can't actually encode RBP with this mod rm stuff, I believe. And if we want zero-based displacement addressing, then we can't do that. Instead, we'll have to use a SIB version of it. And to show you what it was replacing, we have this page, right? And I think it might be easier to see what is going on in here. So yeah, this is mod rm, and you use register 101, which is displacement only mode if mode is 0. So it is actually a SIB byte encoding, I guess. No, actually it is just mod rm. So we do, yeah, mode 00, rm is 101, and this was previously displacement 32. So this is what they say, and previously it was displacement 32. Now it's RIP plus displacement 32. It is also connected to the fact that I was talking about security reason, but one more reason is since we now have 64 bits of memory, and at the same time we don't expect the executable to be that large, we can keep 32-bit displacements instead of moving displacements to 64 bits to allow this direct addressing. Anyhow, let's try to figure out how we're actually gonna do this stuff. So the first thing that we will need is to have some kind of test case, right? Let's add it at the top again, so it's easy for us to test this. And it should support RIP relative addressing. I'm not exactly sure how we're gonna check that this works, because we will be replacing our absolute addressing with relative one in certain cases. So I guess we can only do like really checking the encoded bytes, which I don't necessarily want to do, but I guess we'll consider test passing if it just doesn't crash. Okay, so we have function return 42, and that function will do return value from S32 42. That's good. And we have function proxy, and this thing will return call function value return 42 with what do we pass to call function value? I always forget that. Call function value, builder overload, and then array. Okay, so that's good. Means I need builder, and I will need to do this, maybe get a single overload return 42. Probably makes sense to split it across lines now, so it's a bit more readable. Now I want to have the actual argument, which we don't have, so we can do 0, 0. Okay, first let's check that this actually works. For that we need value as function. Let's do that. So I have the same setup here. We can try to change this to 32 and then check that the result is correct. Oops. Unexpected end of file in macro. That's fine. Incompatible types from value overload to value star. Checker value and declared identifier. It's going to be checker value. That's fine. Who is value overload? Who is value star? Builder overload. Oh yeah, okay. So this actually does not need to be overload. This needs to be regular value. Okay, so this builds. Let's run tests. So it passes. That means that currently this code works. But if we look at how this code works right now, we will see what needs to change. Let me scroll to this thing, and we stop in here, go to disassembly, and let me just step into this. So the way that works right now is we have this absolute address of the function. We load it into arrayx register, and then we just call arrayx. And what we want to have instead is essentially, let me step to here, and we can even figure out what exactly we want to have. So we have instruction pointer, right? This is reap. Now we do minus, or actually other way around, we take this constant, we minus reap, and if we remove hexadecimal display, this is not nice. So what I want to do now is convert it to int, cast it to int, Okay, and now I can disable hexadecimal. So this is what it should be. We will take current, actually it won't be 43, it will be more, because when you're talking about relative instruction pointer addresses, this is sort of the same thing as with jumps, where you actually, as this constant here, you would use the value of instruction pointer after this call is executed. So actually it should be like this. So we take the address of the next instruction and we use that as the stuff, right? So this would be minus 46 because this instruction is 3 bytes. And this should be fine. Okay, so now we know what we have. We know what we want to do. Let's dive into this. How can we make that happen? Whenever we do call function value, we need the actual implementation of this. Where are you? Okay, somehow I'm messing up this. Okay, this is the implementation. And in here we call function overload, which we now bookmark. And this is what we see, right? We have this move of address to arrayx, and then call to call of that arrayx register. And now we need to replace this. And I'm not sure exactly where to put this logic. I guess we have to put it here because at the time we come to encoding, it's a bit too late. Like encoder should not really know how to do this unless we want to do this dance in the encoder. So I'm not sure which one is the right way, but we'll just put it here for now. And what do we put here? Well, we have the builder. So if we have the builder, that means that we know the range of memory that is inside of those boundaries, right? We know that whatever is the range of addresses, because we have this builder.memory or builder buffer memory. This is the start address, so we can do stuff like S64 start address is this. We convert it to S64, and then we have end address, which is start address plus buffer size. So capacity, I believe it's called. And if the address is within those boundaries, then we know we could use relative addressing, because we know that they are in the same memory and they are within 32-bit range, because like we don't use that big buffers anyway. Like we're not going to generate 2 GB executable, at least not anytime soon. So this is fine, and we can do the check and say if so we want to have this to call is a scriptor type function, yes, and we have this move value here, and we need to do some checks. If to call operand type is operand type immediate 64, because we cannot do this calculation if we don't know the actual address. We only can do that for statically known things. So we can move this. Actually, no, let's leave it outside. And now we need to check that address is in bounds. So we do to call operand immediate 64 is more or equal start address, and to call operand immediate 64 is less or equal, actually it should be probably strictly less, but it doesn't matter, end address. Then we can do stuff. And right now, instead of doing stuff, I just want to figure out if we are hitting this case, like, is my logic even correct? So let's just do standard printf debugging session and run the tests. Okay, so there's a bunch of places that are hitting this. That means that we do have things that we could encode as RIP relative. Okay, so I guess we will need to introduce a new operand type, because our encoder actually needs to know about these things. As I said, because we'll have to patch them in or do some kind of look ahead calculation, because when we're calculating the address, we need to do that as like after the instruction has executed. So we need to take address of the next instruction as the base. So let's just say that else is like so. Okay. And what do we do here? Well, we don't need to move value. Instead, we create a new operand, and we say operand RIP relative is well, type would be operand type RIP relative, and for the value we need to have let's explicitly call it RIP displacement, so we don't accidentally mix up with something else. And displacement would be this thing minus start address. Or this is actually an interesting thing, because maybe we should treat this as simply memory indirect operand and handle it there, handle it in the encoder like with everything else, and just treat this. I'm not sure. So the problem with this calculation is that this is incorrect. Like right now, it will just tell us what is the offset from the buffer, but we need offset from instruction pointer, and offset from instruction pointer is something else. So I guess the address here won't really change. Let me think about this. So we have operand types. So we have these memory indirect, and the RIP relative addressing is actually takes over the BP register and uses that for the address. Let me just verify that stuff, right? So RM will be 101, so it's RBP, and mode will be 0. So we'll use this mode displacement, and we'll use this thing, but at the same time it will do something else. I'm not sure what is the best way to deal with this. Let's just shove here yeah, let's just put here a boolean right now. I don't think that's a good way to deal with it, but let's just make something happen. Is reap addressing, and if that's the case, then no, I don't like that. I don't like that at all. Let's continue with the original plan where we are using a separate operand type and then figure out how to deal with it. Okay, operand type reap relative, that's good. That's fine. And then we need to have this. I would actually say that we directly use immediate 64 as an address. Yeah, that's perfectly fine. That would work. So this will be just a hint to the encoder to do something different. And now we say call reap relative. Let's see if that builds. I actually updated my Visual Studio C++, and it added this new warning, which actually is quite nice, that checks that you exhaustively go through all the switch cases. So that's good. Let's do it. And this function I'm editing right now is just it turns the operand type to string. So I can do some more debugging, and actually we'll probably see it right now in action. When I run the tests, it should fail and should tell us that it cannot find the encoding. Yeah, so exactly. So it says, oh, I cannot find the encoding for this reap relative stuff. Good, well, that's what we sort of want to. But I think I'm doing the wrong thing. Yes, it should be like this. We're just directly moving stuff. Okay, so the first thing is it needs to decide that it knows how to encode things. And we have this correspondence table kind of, which probably should actually be a lookup table instead of this gigantic switch statement, but it's fine for now. And what we want to do is say if operand type is reap relative and encoding type is register memory, then we know how to do this, right? So then this is okay. But we also, so now it should actually do something, but the test will still fail because it will output complete bullshit, I believe. Yeah. It fails in here, so it tries to do the encoding for this reap relative addressing, and something is not correct. So let's add a separate if. If type is operand type rep relative, then we do something. And also, like with this code now, you see the value of assertions, right? They just sort of guide us all the way of what we need to do once we introduce a new concept. Okay, now we look at this thing and we know exactly what to put in where. So we know that our M is supposed to be 0B101, and we are not referring to register, so it's actually like it's okay for us not to use a constant here and put in a magic number because it is a magic number. And then mode is 0. So these are the things that needs to happen for rep relative. But another thing that needs to happen is we need to encode the displacement, right? We need to write that out somewhere. And right now the displacement is happening here. So we will need to add a branch here as well. So that will do this logic. Okay, what is happening here? We will definitely need to append some value. So let's just say that we will have this displacement which will be S32 displacement, and we will write that out. But how do we calculate that? So again, we know the address. We checked that that address is within the range already. We could re-verify it here. I guess it doesn't really hurt us to do that. So maybe let's do that. So we get this stuff into here again. And then we, instead of just doing an if, here it is an assertion, right? We're saying you told us to encode this stuff as rep relative, but if you did, you better make sure that we actually could encode it that way. So we say operand immediate 64, or should be like this, is more than start address, and it is less than the end address. Okay. I guess it's not builder buffer, it's just buffer. Let's see if it builds. It does build, but I don't want to run it yet because we still haven't done the calculation. And the calculation is a bit funky. So we say currently occupied bytes, or let's do this. Next instruction address is buffer, or is start address plus buffer occupied plus size of S32, right? Because it said we need to be after the current instruction, but we know that the size of displacement is 4 bytes, so we can just take the current offset in the buffer where we are writing out the instruction bytes and add that add those 4 bytes here, right? So this is next instruction address, and this is what we are actually going to be using for displacement calculation. So let's move this displacement now here and say that displacement is our start address, or sorry, our operand immediate 64 minus next instruction address. And that value, as we saw in Visual Studio, like when we were doing debugging, that value can be negative. So we have these plus minus 2 GB offsets, as it says here in the documentation. So this should be correct. Conversion from S64, yes. Well, let's be good people and do it this way. We probably want to have some functions that's like checks for overflow when converting numbers. I'm actually not sure if you can enable this as a compiler thing to like do that for you. But for now, let's just add it manually. Whatever. I will look into how to enable it in the compiler because it will be quite messy. Let's just cast this stuff and hope it doesn't overflow. Okay. Let's run the tests and see how badly we fail. Wow, apparently we do fail quite badly. So this is a good point to start debugging. Luckily we have this nice and small case to reproduce the problem. So we go into this stuff and it did not seem to do that well. So we are actually no, that seems kind of okay. Let me check what it disassembles to. Let's use this website and disassemble this thing. So that seems actually quite correct. So I'm actually maybe not, or maybe yes, or maybe not. Yeah, that seems actually fine. So we call this address. This is this thing, and what exactly is wrong? I wonder. Access violation reading location -1. I'm confused. Okay, what if I just do the opposite? What if I try to assemble this? 1 byte, 2 bytes, 3 bytes, 4 bytes. Not sure what that comment means. Oh, yeah, that's actually very incorrect from what it's trying to do. We don't want to call whatever is in the memory here. We want to call that memory. So but this encoding is correct. I'm not sure about this syntax here, actually. Let me also check it in the remedy debugger and see if it shows us the same thing. But I think it can't actually step into this code, if I remember correctly. So that would be unfortunate. Yeah, it can't really step into that code. But it shows the same error, of course. Well, let's think about this. How does reap relative call look like? Can we have a reap relative call? So let me do minus whatever 32. So what is that? Sample 2. Since instruction seems correct to me, let's check again. We go inside of here. Can I do it like this? No, that's not a valid way to write this stuff. And if I do it like this, I still have the same instruction. Oh, but it actually uses a different encoding, which is interesting. So here we have FF15D9 and no, this is just address. So it is FF15. Okay, that is a bit of a bummer. Now I need to figure out where to move from here. Well, let's start with rechecking everything. This is the right address. This is exactly where the other function actually starts. So the encoding seems to be correct as far as offset is. But if I understand correctly, instead of going to that location, it kind of tries to, I don't know, use this as an address or something, which is not what we want. Can I change how it shows this stuff? Show address. No, I do want to show address. I want to also figure out how to force you to show line numbers. No. I'm a bit bummed. Let's read what this thing says. Model RAM and SIB subfield encodings. 64-bit model RAM. This encoding is redefined as blah blah blah, rather than displacement only. There's no dependent suffix. So that just says about R13 stuff. Okay, yeah, that makes sense. Reproductive addressing is enabled in 64-bit mode. We are running 64-bit mode. So what is wrong with you? I wonder. can we find a rep relative call somewhere in here? Can't search in disassembly, which is a bit disappointing, to be honest, that you can't search in here. I wish it was treated as a regular file and not this weird thing. RSP, RSI, RSP, RTI. I just do this. And search here. Say rep plus. Rep. So I actually want this. No, there is no such thing as rep in here. Okay. So this seems fine. We say we want, can I do something like this? I think there is this different syntax for specifying, like I want offsets of 32 from register, but I don't remember what it is. I think we can see it here. Actually, yeah, that might be a good idea because this will actually show us what it's supposed to look like. So let's do that. We have this code over here, and I will literally just implement the same functions as we have in our test in the compiler explorer and see what we are doing wrong. We have int return 42, which, well, returns 42. And then we have int proxy that just returns return 42, right? This is the exact same thing as we have over here. Well, this is not particularly useful because it uses labels for all of this stuff. And I wonder if it's possible to somehow force it to show us the actual thing. Although, okay, let's try to copy this in other version that is not MSVC, and maybe it shows the assembly syntax slightly different. So this stuff, can I just do this? Well, I think, okay, so this is good. This means I can look at how this is done. But this does not really use the rep relative addressing, right? If I disassemble this, then yeah, it's just it's calls some direct displacement. Are we using, yeah, we're using x64 here, but this is not what we are getting. Should be like this. So let me open this in a new tab so I don't overwrite this, and let's again look at this stuff. Sorry, disassemble. E8, EC, and now I want to look at the call instruction and see what is this version. Call near relative displacement relative to next instruction. Oh, okay. So it's just actually me being stupid. Call has a special mode for this, which has nothing to do with rip relative. I mean, okay, let's put it differently. For call instructions, we need to use different encoding. So what shall we do? We definitely should fix that, but that means that we are not actually going to be using relative. Instead, we will put immediate here, and immediate just does a different thing from what we were used to. I guess we have this code for jumps somewhere, and actually jumps, we deal with them in not in the encoder, but we deal with them in the main builder stuff. So that's slightly different direction from what I wanted to do. What shall we make happen then? Okay, I guess let's make that work. We don't do this in call. I will add a fix me here that says fix me do relative address, and instead we will actually now use rip relative for some operands. And this is not how it's supposed to be, but that's perfectly fine. So first of all, let's uncomment this, let's build this, and address is not used, that's fine. We will come back to this. And what is, yeah, so we are running the file, which is why we can't build. This is why everything's fine. Run test now should still be fine because we are not actually using our code path, and we need to slightly change the test. So this stuff doesn't work with functions, or rather it works slightly differently. So we want to have some value that we will put in that we can use this addressing with. And the way I'm going to do this is I'm just going to say that the function buffer occupied is size of, or actually even better, I will say buffer append as 64 or as 32, that's fine. Buffer append s32 function buffer, and then 42. Okay, now I will create a value with this address. So I say value overload star static value, or let's call it ref value, is function is what? It is going to be this thing, and we say as immediate 64, we use S64 of function buffer memory. So we are pointing just at the very beginning of the function buffer. Print every relative. No, this is not what we do anymore. We need to do it this way and this way. And here we say operand. Here we say descriptor, and the descriptor will be descriptor S32. That's fine. Okay. We have rip overload. That's fine. We have value rip value is a single overload value of rip overload. Okay, so just to clarify what we did here, we have this huge chunk of memory, and where we usually would just write code to, but now we are reserving 4 bytes at the top and putting value 42 in those 4 bytes. And then we are creating a value that we can use in our calculation. And now we will do this return rip value. We don't need this thing anymore. We can do it this way and see what happens. I cannot spell descriptor correctly, which is perfectly fine. And now we can look at what changes. Okay, so we look at this stuff. Actually, that was fine. Well, at least it encoded something. And we can look at what it encoded. So now that's exactly what we want, I hope, at least. So as you can see, it does the same calculation. I really hate that it doesn't show that this is a rep relative encoding. Like, it's just, I don't know. It's very bad for debugging. It's just directly points to this address and you don't know, like, did my assembly actually specify a absolute offset or relative offset? Like, what's happening here? I guess it expects you to know that in 64-bit mode you cannot specify like direct offsets. Anyhow, the point is that if you look over here at these 4 bytes, they're not interpreted as, they are interpreted as instructions, but this is not how we are interpreting them. We are interpreting them as a single value, and if I just point to this value, it should even say to you that this is 42, right? So if we now step through this, and we will be ready, and if we look into our return register, so inside EX, we have 42. Good, so we are successful in this code. We did not break anything else, and everything is fine. Okay, so there was a bit of debugging involved, and I think it's actually good to showcase that people forget stuff, because I did this a long time ago. Like, I played around with this rep relative stuff, I guess, almost 2 or 3 years ago, so I forgot everything, but now we know that we also need to implement this version. And like, you can still call rep relative stuff, so maybe I should fold it into this RM calculation, but maybe not. And you can still do this. Also, just as a side note, we could use rep relative later on for forward declarations. Obviously, that's not how C actually does them, but we could use it for that. Anyhow, let's see again. Tests are passing. Everything is great. We have our rep relative addressing. We figured out a bunch of stuff, and we are ready for the next thing, which will be tomorrow. For today, I'd say thank you and see you then.